Thank you very much for that introduction. And thank you for Hendrik. Thank you, Hendrik, for for a lot of things. I mean, not just having not just being the occasion for this meeting, but also I mean, I don't know how many of you know, but I learned algebraic geometry from him. I won't say how many decades ago, but it was a long time ago. All right, so here's my title. So I'm going to talk about integral points on curves. The Baker's method and finite étale coverage. And actually, my talk is mostly about how you cannot find integral points on curves using these relations. But anyway, so let me start by talking, well, somebody who's already been mentioned today, Siegel. Let me talk about Siegel's theorem. All right, so okay, before I state what Siegel proved, I want to remind everybody what the characteristic is. And so let me first talk about it for a curve over the complex numbers. So this is going to be a smooth affine curve, and so it'll be a smooth projective geometrically, or smooth projective integral curve. So I'll just say nice curve, minus some finite subset of points. And so okay, so this curve is a nice curve of, let's say, genus G over the complex numbers. So if that's what U is, so U is going to be some smooth affine curve, then and this is going to be non-empty. So maybe I should write it now. So then the Euler characteristic you can compute as the Euler characteristic of x minus the number of points of R. And so that's 2 minus 2g and minus the number of points here. Okay. So okay, now I can state the actual theorem. So now instead of working over the complex numbers, let me work over the number field and take the I want to talk about S integers. So let's take a finite set of places. So finite set of places and containing all the Archimedean ones. Median places, and then I can take the ring of S integers, which I'll just call O. So those are the elements of the number field that are integral at all the places outside S. So okay, so these are evaluations and so on. And all right, and then U will be defined to be a smooth affine curve. Smooth affine geometrically integral curve over K. And then and by the way, the smoothness is not a big deal for the sake of finding integer points. You can always replace it by its normalization. So it's okay. And now so now here's the theorem. So it says that if the Euler characteristic of U base change to the complex numbers is negative, then the set of integral points, well, you have to choose some model to talk about integral points, since I only had a U over K, but okay, then this is a finite set. Yeah, so this is okay, so this is, I don't know if you notice, there's a little tiny little circle thing on that U. So that means it's a model over O. So okay, so this is some O, this is any O model of U. Okay, so and maybe before maybe I can also discuss an example. The maybe the prototype for this is if you take U to be projected line minus 3 points, which might as well be 0 and infinity. Well, then this you can also think of as being instead of the curve defined by the equation x plus y equals 1 inside the multiplicative root across itself. Because if I draw, oh, okay, let's I don't want to make those axes solid because they're not part of GM cross GM. So they're what not there, what was not there. But then I take the x plus y equals 1 and I get a line with 2 holes in it. Yeah. And you can see, yeah. So if that's so this x plus y equals 1, and if you project onto the first coordinate, you see that you get the affine line minus 0 and 1, which is this. Okay, so that's a curve, and you can calculate the Euler characteristic. So then the characteristic of this curve is, well, it's 2 minus 3. And yeah, that's negative. Yes. So okay, so that means that the set of integral points is finite. So, and what is the set of integral points? So it's, well, if you take the usual model, P1 minus these 3 points over there, then this is just going to be the set of it's this set of pairs of units that add up to 1. So this is the, yeah, so this is called the S unit equation, and it says that so the claim is that it's that, yeah, so this, okay, maybe, okay, sorry, I should have, okay, so the set is finite. Okay, so, well, I mean, the problem with Ziegel's theorem, as I'm sure you all know, is that it's not effective. There's no known algorithm that takes as input the equations of U, and actually, even in the case where it's finite, there's no algorithm known to find to print out this list of integral points. And so, at least in the general case, there's so one of the few positive things that's known is what comes out of Baker's method. So this is a method based on what's also called linear forms and logarithms. Okay, so what does this let you do? So maybe first, let me write down one version of Baker's theorem, and then say what it lets you do is how it connects to integral points. So okay, so the theorem is, well, for this version, if I'm given A, which is a number field, and I choose an absolute value on K, so it could be an Archimedean one or or coming from some p-adic valuation, something like this. And then I have a list of elements, alpha 1 through alpha n, in this number field. Yeah, let's put it again, non-zero, and have some epsilon, some positive real number. Then there exists a constant. So and this constant is effective. Such that if you have an almost multiplicative relation between these numbers coming from, okay, so these are going to be exponents, and let me give names to the maximum of these. And if these satisfy the equation that if you take these powers and multiply them, and you compare how close they are to 1 using this absolute value, if it's not actually equal to 1, then okay, so if you have an almost solution, meaning that this difference is sort of exponentially close to 1, then, well, it's basically saying that there are only finally many solutions, and that then the solutions are bounded by that C. So then So that means that in principle, if you're given all these data, you can actually find all the solutions to this inequality. You can all find, yeah. Okay, so, and from this, I'm not going to go into the details, but from this, if you apply this where the alphas are the generators of the unit group of this ring of integers, then you can show that if you have a solution to this S-unit equation, then you can use that to get examples of processes that are extremely close. So as a corollary of this, you can prove that this set of is not only finite but also computable, effectively computable for certain u. For certain u, and this for example, it works for the unit equation x plus y equals 1 in GM cross GM, but also a few others. And Yuri Bilu generalized this in his thesis. So when he generalized how many the class of curves to which this could apply. So this is from 1995. So what did he so he proved that if U has a non-degenerate morphism, I'll say what this means in a second, to the product to GM cross GM. All right, okay, let me write down what this means. So U again is the affine curve, and non-degenerate means that it's the image in GM cross GM is not contained in a closed set of a smaller algebraic group, of a closed set of a proper algebraic subgroup. Proper in the sense of not equal to the whole thing. Well, actually, I guess it wouldn't be. Okay, yeah, that's right. Okay. Okay, so yeah, so for example, I don't want you to do something like, so not something like, I mean, inside here you have a subgroup defined by y squared equals x cubed. But I would not want you to take a curve like that, because a curve like this could have instantly many S-unit points on it. So okay, so if you have a U like this, then Baker's method applies, and you get the theorem that you want, that this thing is, well, not only is it finite, and that just comes from the Ziegel's theorem, but it's also computable. So yeah, okay, so and then the question is then to which curves does this actually apply? I mean, if I give you an affine curve, can you tell? Well, can you figure out whether it has such a morphism? And well, yeah. So is this still readable when I write down here below? Maybe I'll switch things. Okay, so to which U does this apply? I mean, you can rewrite this condition in more intrinsic terms, in terms of, I mean, essentially what you want is, well, I mean, to give a morphism from U to GM cross GM, if you pull back the coordinate functions on GM cross GM, you get two rational functions on U, two units, two invertible rational functions on U. And so you need that the group of units of this algebraic curve, well, modulo the constant functions. So modulo the constant. You need that there should be two independent functions, and you want them to be independent, multiplicatively interdependent, in order for it not to be contained in a. But essentially, you're saying you want something like this. And another way, yeah. So So this is a condition that's something you want. And there are other ways of saying this. This is basically the same as saying that there are two independent principal divisors on the that are supported. So principal on the projective closure on the X, but they should be supported. I mean, in order for them to be units on U, you would need them not have any poles or zeros on U. So the divisors should be supported on the finite set R that was removed from to get to. And you can also say that's the same. I mean, if you just think about those divisors, and if I gave you two divisors for an R and I ask you, are they principal? You can also check that by adding them up in the Jacobian. And so this is also the same as saying two independent relations between among the points of R. Points of R in relations between them in the Jacobian of X or in the Picard group of X. Yeah, and this is something you can actually test. If I give you the curve, if I give you the X and the R, you can actually test what the relations are between those points. Okay, so that's good. But I mean, of course there are many U's for which this is not. You do not have this. For example, well, one example would be if R just consists of one point, then they're not going to be. You can't use this method directly. But there are other things you can do. You can combine this Baker's method, Beal's generalization. You can combine that with the method of finite étale covers to try to enlarge the applicability of this method. So let me talk about that next. Yeah, by the way, feel free to interrupt me. Any if there are any questions, yeah.
So you said that it's easier to decide whether these relations exist. So I mean, of course, if there is a relation, you can write down the function with that divisor. But is it easy to prove that there isn't some relation with extremely large?
Yeah, you can do that. You can do that as well. I mean, if you're given a bunch of points, it's essentially the trying to decide, given a bunch of points in the Jacobian of the curve, what the relations are between them. And yeah, you can do that based on given the heights of the function. You can bound a priori how big the integer combinations of them would have to be. All right. So okay. So there are some kind of reductions you can do to if you don't like the curve you started with, there are things you can do to replace it to hope, and hopefully you can make these conditions hold for the new curve. And well, okay, there are other simpler kinds of reductions you can do. For example, you're always free to enlarge your number field and to allow, I mean, to relax the integrality conditions by enlarging S. I mean, that's not going to help with those conditions. It's just going to make it worse. But yeah, you can. Okay, so you can do this. Okay. But there's also the Chevalier-Vey method, which is sometimes also called descent, which actually I'm not sure if they stated it for integral points, but I mean, it's the idea is basically there. So if you start with your U and you have a finite étale cover by another curve U prime that's of the same type, so another smooth affine curve. Okay, let's call this morphism pi. And so if you have such a thing, well, then the integral points on U will be contained. Well, it's not necessarily true that an integral point here will lift to an integral point here, because this involves solving some equation, but it will be true after enlarging the K and the S appropriately. So for some for some computable O prime. So for some so a priori computable O prime in some larger number field possibly. And so that means if you're trying to solve the problem for you can reduce the problem to, you can replace your curve by this at the expense of enlarging your ring. But that's good because this upstairs curve has maybe some even if U doesn't satisfy these geometric conditions, maybe this cover will. Yeah. So okay. So that's computing. U O. We can one time place. U by U prime. And so, in fact, this idea already, this is enough combined with Baker method. These already handle all cases where the genus of X is less than or equal to 1. And also some higher cases as well. Some higher genus curves too. So I mean an example of this. For genus 1, I mean there always has to, I mean in order for the Euler characteristic to be negative, there has to be at least 1 point removed. So the hardest case is where there's just 1 point removed. So suppose U is just sort of an affine elliptic curve. So the affine elliptic curve with 1 point removed. So then what you can do is you can look at the multiplication by 2 map on the elliptic curve, which will be some finite étale morphism. And you can look at the part of that that's above U. And so then you'll get some U prime, which, and if you just take the inverse, you'll get a curve that now has 4 points removed. But the good thing about this curve, I mean, here there's no hope that Bielow's condition will hold because there's only 1 point removed. But now there are 4 points, and there are relations between those 4 points in the Jacobian, namely they're all 2 torsion points. And so you can find these 2 independent functions. So like, well, if you use the standard test equation, and E1, E2, E3 are the roots of the f of x, if your curve is y squared equals f of x, then you'll have these 2 independent rational functions whose divisors are supported on that finite set of 2 torsion points. And so that's what makes it possible to use Baker's method on this curve. And this is why, well, this was already observed by Baker, that you could find the integral points on curves, on elliptic curves in this way. Okay. All right. So the question is, I mean, the question is how many, I mean, what are the curves to which that can be handled this way? And so I think, yeah, so the big questions then are, so let's formulate this. Okay, so the first question is, maybe it's true that you can this always works for every curve. So does every smooth integral affine curve? Yeah, and I'm always, in checking these conditions, I can always enlarge the number field. So I might as well just say, and I'll just restrict your attention to curves genus 2, at least 2, because genus 1 is already done. So, all right. So let's say over Q bar, so it doesn't really matter which number field. Does it always admit a connected finite étale cover? With a non-degenerate morphism. To GM cross GM. I mean, if the answer is yes, that means, well, then we have an algorithm for integral points on all curves. Yeah. And you could ask also, let me also make a stronger version of this question, stronger. If you notice in this example, not only was this an étale cover of U, but it was an étale cover that came from an étale cover of the projective curve. So I can ask, you can ask whether that's always possible. So it's same question. Yeah. Those are those three lines. And but it's not, I'm not done. It's all those three lines except for the question mark. Yeah. It's to be precise. Yeah. That line is true. Maybe I should get to make it clear. Such that the cover extends to a finite étale cover. A finite étale cover of the projective curve. Yeah. Of say the nice for me means smooth projective. So okay, now the question mark comes back. All right, yeah. So let me look it up. Okay, so those are the big questions. And yeah, I said it would be very nice if either of those are true. Because that would let you solve the general problem of integral points on curves. But I conjecture that the answers are no and no. So no. Okay. All right. So why do I think that the answer is no? Well, it's because I can prove well, I can't, I mean, those are conjectures. Maybe I can make okay, but so the reason why I think the answer is no is because I can prove a weaker version of one of those. Okay, so here's what I can actually prove. The theorem. Okay, what am I? Section 5. All right, so the first theorem is that if instead of Q bar, if I replace it. 4 is up there. Yeah. Okay. Reminded me once when I was giving a seminar at Berkeley, I was drawing, I think for some reason I had to draw a picture of the kinetic numbers or ZP. I was drawing ZP and I was doing it like this to to denote all the different recipe classes, and Hendrik complained that 4 was not prime. All right. So, all right. So now, yeah. So I guess this is payback now. But 5 is after 4. Okay. All right. So. Okay. So if Q bar is replaced, wait. I don't need the bar. So Q bar is replaced by C. Then. In these questions, then the second, then the answer to the 2 is no. All right, so that's, and okay, so that's going to be one of the main theorems, and there's a variant of it. So more precisely, what I'll prove is that given any curve over the complex numbers of genus at least 2, I can make an affine curve by removing just one point. I can remove a point from it. From any curve, I can remove a point. such that the answer is 2, I mean, such that the condition in 2 fails. So fails for x minus x. So in other words, such that there you cannot find a cover, a nice cover of x such that the part of that cover above x minus x has these two these non-degenerate morphisms with GM cross GL. I mean, another way of saying that is that if you take any for given x, I can find this point little x such that if I take the preimages of x in any finite étale cover, those preimages, you will not be able to find two independent relations between those preimages. And in fact, I can say even stronger is that given the x g is greater than 2, there exists and such that there's not even one relation. So that for every finite étale cover, every finite étale cover, say y going to x, the preimages of this point. So okay, so given the x, I can find given the capital X, I can find a point such that its preimages in any finite étale cover are independent. In the Picard group of y. Okay. And yeah. So okay, so these are each one of these is slightly stronger. I mean, each of these implies the previous. Yeah, in fact, they're all going to be implied by this other theorem. Which is what difference? I'll give it a new letter. So this one works. This theorem works for any algebraically closed field of characteristic 0. So these are instead of just complex numbers, and but this is just for one finite cover. So given this a non-constant morphism, of nice curves over K of genus, of genus at least 2. So let's see. Okay, so given that, then there exists a point whose preimages y are independent in this extension. And so this the reason, well, so in fact, I mean, for each well, the reason this implies the previous one is that if you look at the set of points, I mean, the set of bad points, the set of x for which, maybe I'll write this stuff. So in fact, is this visible? No, you don't like it. Okay. All right. Better. All right. In fact, if for each, well, if you wanna prove A prime, I mean, A double prime, I mean, there are infinitely many finite étale covers to consider, but I mean, they're only countably many. So, and for each of the countably many. So finite étale covers Y that you have to consider in this conclusion. The conclusion here, the pre-images are in Y are independent. The pre-images of X of the little point. Then that conclusion fails. For only countably many little x, and so altogether you have only, even if you're trying to make a statement like this for all finite étale covers, there's still only finitely many. I'm sorry, there's still only countably many altogether. There are only countably many bad choices for this little x, and so over a field like the complex numbers, you can always find a good one. Okay, so. All right, so that's why. So this is the proof of that B implies not A double prime. Okay, so the only thing left to do now is to explain why B is true. Yeah,
Just to be clear, theorem B does not require K to be uncountable. Correct.
that's right. So so the proof. I mean, I guess I could have stated. I mean, it would have been enough to do this for the complex numbers, but I can actually prove this in general. So I did. That's right. Yeah, it's more, in fact, yeah, it's more interesting. Well, maybe it doesn't make too much difference, but yeah, it's more interesting when it's not. Okay, so I've got a few minutes left for proving B. So let's do this. Any questions about anything here? Okay, the first thing I can do is I can reduce to the case where Y, where this is a Galois cover of X. This statement I'm trying to prove only becomes harder if I go to a higher cover. So let me do that. So okay, so this is now okay. Okay, so without loss of generality, Y over X is this homomorphism X F. This is Galois. I mean, possibly ramified. So maybe ramified. I didn't assume here that. I mean, and B, this morphism doesn't even have to be étale, finite étale. Okay, and let's give a name to the Galois group. So let's say the Galois group is D. Yeah, and then I can map Y to its Jacobian. But I'd like to do it in a way that respects automorphisms. And so instead of choosing a base point, which may or may not be fixed by automorphisms, I will sort of try to choose a more canonical map here. More canonical meaning I use a canonical divisor as sort of my base point. So that means I have to do something like I mean, the only problem is that the canonical divisor is not degree 1, so I have to multiply whatever the degree is. So it's like some sort of modified Jacobi map. So this is the canonical divisor. This is the degree of the canonical divisor, and so this is a degree 0 divisor whose class is something here. Yeah, and just for simplicity, I mean, the disadvantage of doing this is that this is not necessarily an embedding anymore. For example, if you had a hyperelliptic curve, then all the Weierstrass points would go to this, it would go to the origin. But okay, but for this talk, let me I mean, just so I don't have to, I mean, I don't have to worry too much. Let's just suppose it is. I mean, it's, at least it's gonna be, it will be finite to, it'll be finite to one. I mean, it'll be birational onto its image, but let me just assume, just so you don't have to simplify language, let me just assume that Y is actually embedded in J this way. Okay, so. Okay, so now the question is, how do I find my point little x? Whose preimages are going to be independent in this cover. And actually, I'm going to find my x by finding the point upstairs first. So I need to find a point, it's basically the same thing. So I need to find a point little y, and what I'm going to choose is a point. I want to prove that there is a point upstairs that lies outside every algebraic subgroup. Every algebraic subgroup. H in, yeah, so okay, so every algebraic subgroup of the Jacobian. So I mean, this actually I could have made my life easier by just doing this over the complex numbers, because there are only countably many algebraic subgroups. They're all defined over K. And so, well, I mean, so if K are uncountable, then those countably many subgroups could not cover all the points. So it would be easy to find it, but okay, well, but I can do this also for, yeah, but let me sketch the proof that works even when K is something like Q bar. Yeah. Question?
Like subgroup is connected, or
I'm no, not even necessarily connected. So I'm yeah. So I'm also want to get outside all the torsion cosets of connected algebraic groups. So yeah. Yeah. So right. So yeah. So I'm proving the stronger statements. Yeah. Okay. So first of all, you can reduce to the case. I mean, everything is defined over some finely generated field. So I might as well assume that K is a finite just replace K by the algebraic closure of the field generated by all those finely many things. And then you can, the advantage of doing that is that now I can embed this K into into QP bar for some prime. And then what we end up proving using arguments that are similar to those in a paper I wrote with Devesh Malik. We can prove that, so, sorry, this is, yeah, so anyway, so, I mean, that was a paper about narrow sphere group. What I can prove here is that if you you can find not only can you find a QP bar point that's outside all this subgroups, but actually, if you look at the points on Y that do lie in one of these algebraic subgroups, then it's nowhere p-adically dense. In the set of that means that every non-empty open subset of this contains a smaller open subset, non-empty open subset that contains no points, completely misses all the algebraic subgroups. Yeah. Okay, so you prove that this is true, but also on the other hand, it's also true. It's just a general fact that if you take the points of K, this algebraically closed field, this will be p-adically dense in the QP bar points. And so that tells you that, well, I mean, you find a little open subset here that does not meet any of the algebraic subgroups. And then inside that little open subset, here, you can find some K point. And so that's where this Y comes from. Okay, so that's the proof of a sketch of proof of that. Okay, this requires some work, but I don't have time to talk about it now. But But once you have that, then the. Okay, so, wait, is this a? the black one? I don't know. I know, but, okay, anyway. You just play it safe. All right. Well, no, okay, let's live. Okay, so, all right, so let's see, so, all right, so now I want to finish the proof of theorem B. Yeah, what do I need to do? I need to find a point, well, X downstairs is going to be the image of a little y, whose preimages are independent. So I'm going to choose this y, as in this lemma. And let X be its image downstairs in X. So then if I take the set of pre-images of that point in the cover, that's just going to be the Galois orbit. That's just the orbit of Y under the Galois group. Yeah. So to say, if the pre-images were dependent, if the pre-images are dependent, what does that mean? Are dependent. Then, well, there's some integer combination of these points that gives 0 in the Picard group or in the Jacobian. So there exists some non-zero s in the group ring, such that s applied to y gives 0 in the Jacobian. Okay, but I mean the kernel of this S S gives an endomorphism of the Jacobian, and its kernel is some algebraic subgroup. But I chose Y, so it was outside all the algebraic subgroups. So the only possibility is that the kernel of S must be the whole thing, because that was the one algebraic subgroup that Y is allowed to be in. So by the choice of Y, it must be the S. If S kills that Y, it must kill the whole Jacobian. So Sj is equal to 0. And so that means that S also kills, I can pass to the tangent space, the algebra on which is a representation of G, and S kills that group element kills that as well. On the other hand, there's a still doesn't quite feel like a real black. Anyway, there's Lange and Theisias that says that in this geometric setting where you have a Galois ramified cover of a curve units at least 2, and you look at the decomposition of the Lie algebra of the Jacobian of Y as a representation of G, then it says that every irreducible representation occurs. Every irreducible Q representation of G occurs in the Lie algebra of the Jacobian of Y. But S is killing it. So that means that S must, well, if every that means S kills every irreducible representation. So it'll also kill the regular representation, but that's only possible if S is 0. So yeah, which is a contradiction because we chose that S was supposed to be non-zero. Okay, so that's the end of the proof. All right, so I would like to be able to prove more. I'd like to say that I think it should be true that these other theorems should be true also for Q bar and not just for C, but that's where things stand now. So yeah, thank you all for your attention.